All right, welcome everyone. I'm Athirma here, and for the next few minutes, we're going to embark on a bit of a journey. In this series, we are going to break down the mathematical engine that's really powering these large language models. My goal here is to give you a real intuitive feel for how these things actually work. So let's start with the most basic question you can ask. How on earth does a machine even begin to understand the words I'm saying to you right now? You've probably seen this equation before. It looks like magic, doesn't it? A simple bit of math that seems to understand analogies, almost like a logic puzzle. But this isn't some clever trick. It's actually a huge clue that points to the entire geometric world we're about to explore together. And really, that brings us right to the heart of the matter for today. How do we take something as complex and full of nuance as language and turn it into a mathematical thing, an object like king that we can just add and subtract? Okay, let's dive in. So before an LLM can do any of the fancy stuff, reasoning or writing poetry, it first has to do something much more fundamental. It has to translate our language, the world of words, into its own native tongue. And the language of a computer, of course, is numbers. You have to remember, at its absolute core, an LLM is just a phenomenally powerful probability machine. Its main job, its ultimate goal after all its training, is actually pretty simple. You give it some text, and it predicts what the very next piece of text is most likely to be. This whole translation happens in two main steps. First, we have to chop up our sentences into manageable pieces. Then, each one of those little pieces gets its own unique numerical address. Think of it like a coordinate in a massive mathematical space. We call these pieces tokens. Now, you might be thinking, well, why not just use letters? A, B, C. And the answer is really all about efficiency. It's so much less work for the model to think about explain and as two chunks than to process E, X, P, L, A, I, N, E, R one by one. It also gives the model a bit of a head start because these word fragments already have some meaning baked in. And this right here is the magic step embedding. The best way to think about it is like a giant multidimensional dictionary. Every single token gets looked up, but its definition isn't a sentence. It's a very specific coordinate, a vector, in this huge mathematical space. And when I say this space is massive, I am not exaggerating in the slightest. For a model like GPT-3, the vector for a single token, its embedding, is a list of 12,288 numbers. That's one point of data in a universe with over 12,000 dimensions. It's kind of impossible for our brains to even picture that. So, okay, we've got these enormous lists of numbers, but how do we get from a coordinate to actual meaning? Well, the answer isn't in the numbers themselves, but in the geometry of the space they create. And this is what's going to let us finally solve that king and queen puzzle from the beginning. This is probably the most important idea to grasp about embeddings. It turns out that meaningful relationships, things like gender, verb tense, or the connection between a country and its capital city, they don't just exist as random points. No, they are represented by consistent directions through this high-dimensional space. Let me give you an example. The direction, the vector, that points from the man coordinate to the woman coordinate is almost exactly the same as the one pointing from uncle to aunt. The model has learned a consistent gender direction, and this is precisely how that king-queen thing works. So if we start at the king vector, and then we travel along that gender vector, which is like subtracting man and adding woman, we land remarkably close to the actual vector for queen. See, it's not magic at all. It's just geometry, but in a very, very big space. Now, this whole system, this geometry of meaning, is only possible because these 12,288 dimensional spaces have some really bizarre properties, completely counterintuitive to how we see our normal 3D world. But these strange mathematical quirks are exactly what you need to represent something as complex as human language. But this seems to create a problem, right? There's a nearly infinite number of concepts in the world, from political theories to types of humor, but we only have a finite number of dimensions to put them in. How could that possibly be enough space? Well, think about our 3D world. You can only have 3 lines that are all perfectly perpendicular or orthogonal to each other, x, y, and z. And even if you relax the rules a bit, say they only have to be almost perpendicular, you still can't fit that many more. But something amazing happens when you start adding more dimensions. The answer is just astounding. the number of almost orthogonal vectors you can cram into a space, it grows exponentially with the number of dimensions. This isn't just some neat math trivia. This is the fundamental secret that makes large language models possible in the first place. This exponential capacity is basically a mathematical superpower. It's what allows the model to store millions of different ideas, each with its own unique direction, without them all blurring together and interfering with each other. It's how you can have a clear direction for royalty that's distinct from gender and distinct from everything else. And it's why just making these models bigger, with more dimensions, often makes them genuinely smarter. So what we've described so far is like building a massive, static library of meaning. Every token has its fixed place on a shelf. But of course, that's not how language works, is it? The meaning of a word can change completely depending on the words around it. It's all about context. Just take the word mole. Its initial embedding, its starting vector, is basically a confused blend of all its possible meanings. Is it the animal? Is it a spy in a government agency? Is it a unit in chemistry? By itself, the vector is ambiguous. It holds all these potentials at once. And this leads us to the next big question we have to answer. How do these vectors talk to each other? For instance, how does the vector for the word biopsy tell the vector for the word mole to lock on to its medical meaning? How does the information flow between them to build a single clear context? Well, in part 2 of our series, we're going to open up that black box. We'll explore the core mechanism that makes this communication possible, and it's called attention. This is the engine that allows these vectors to pass messages back and forth, building the rich, dynamic understanding that makes today's LLM so incredibly powerful.